Hi guys, today let's talk about the scalar product, vector product, scalar projection, and vector projection. Now this includes the length of projection, which is a huge point of confusion for everyone. So today there will be a crash course on that as well. In another YouTube video called How to Derive Cross Product and Dot Product, we define the dot product as u dot v, or the scalar product of u and v. Again, these two are the same thing, is equal to u1 v1 plus u2 v2 plus u3 v3, where it's a real number, where u is equal to u1, u2, and u3 in the xyz components, and v is equal to v1, v2, v3 in the xyz components. And we have u cross v, or the vector product of u and v. Again, the vector product, it's called the vector product because the final result is a vector. And that's equal to, now in the first row, it's 2 times 3 minus 3 times 2. So it's u2 v3 minus u3 v2. The second row will be u1 v3, u3 v1, so it's 1 and 3. You get negative of u1 v3 minus u3 v1. And for the last one, it's 1 and 2, so it's u1 v2 minus u2 v1. Now these two have to be committed to memory because that'll really expedite things in the future. And we also defined u dot v as equal to modulus of u times modulus of v times cosine theta, where theta is the angle between u and v. And the vector product is used in sine theta, where the modulus of u cross v is equal to the modulus of u times the modulus of v times sine theta. So we learned that u cross v is equal to w, where w is equal to this whole chunk of a vector over here. So w is the vector that's perpendicular to both v and w. And in some textbooks, they have this weird formula which is equal to, weird formula that's u cross v is equal to product of modulus of u, modulus of v, and sine theta, as well as the unit vector of w. So the unit vector of the vector that's perpendicular to u and v. And from our equation, we derive that u cross v is equal to modulus of u, modulus of v, sine theta. So how do you get from the second equation to the first equation? Now I'm going to multiply the left hand side by u cross v and the right hand side by the vector w. Now that's because these vectors are essentially the same vectors. And from here onwards, I'm sure you can see it by now that you have to divide both sides by the modulus of u cross v, which is also equal to the modulus of w. So it's w over its own modulus, and that gives you its own unit vector. Right? Because this whole line has the modulus of w, and all you need is the unit vector, which has modulus equal to 1. So the unit vector, just to recap, is equal to a vector divided by its own modulus. So these are 5 scenarios that u and v either behave similarly or differently in, whether they are scalar product or the cross product. So the first one is whether u and v can reverse. So what it means is that whether u and v can switch spots and have u dot v is equal to v dot u. So I'm just going to use the first term because the rest of the terms follow the same idea. So we have v dot u is equal to v1 u1 plus and onwards, which is also equal to u1 v1, right? Because these products are the same thing, and therefore this is equal to u dot v. So therefore we have u dot v can be equal to v dot u. Now for the cross product, on the other hand, we have u cross v. So the first column would be u2 v3 minus u3 v2. For v cross u, in the first column we have v2 u3 minus v3 u2, so on and so forth. And that gives you negative 1 times u2 v3 right over here minus u3 v2, which is equal to negative of u cross v. Right, so therefore we have v cross u is equal to the negative of u cross v. And on a visually it makes sense, because then let's say we have two vectors over here, u and v. Where if u cross v, you have the resultant vector up here equal to w. And when you have v cross u, you have the negative of that. So it's negative of u cross v, which is negative w. So it's in the opposite direction to w. The second property is about whether it can distribute over addition and subtraction. So we have u dot v plus w be equal to the first term having u1 times v1 plus w1, so on and so forth, which is also equal to u1 v1 plus u1 w1 plus and so on and so forth, be equal to u dot v plus u dot w. Right, so it distributes over addition and subtraction like so. Now for the cross product, we have u cross v plus w. Right, I'm just going to write the first term down, which is u2 times v3 plus w3 minus u3 times v2 plus w2, so on and so forth, and that's equal to u2 v3. So it's really cluttered here. So the first row, I'm just going to write the first row here, is equal to u2 v3 plus u2 w3 minus u3 v2 minus u3 w2. And you can see from here that it forms two vector products, u2 v3 minus u3 v2, like over here, and u2 w3 instead minus u3 w2. So the final result will be equal to u cross v plus u cross w. So the vector product does distribute over vector addition and subtraction. So now on to the scalar multiple. We have the scalar multiple of lambda, an element of real numbers. So lambda u dot v is equal to lambda times u1 v1 plus so on and so forth, which is also equal to u1 times lambda times v1 plus so on and so forth, which is also equal to u dot lambda v. So the scalar multiple can be given to v and u. So for the vector product, just going to bracket this here. For the cross product side of the house, we have lambda u cross v is equal to lambda u1, lambda u2, lambda u3 cross v1 onwards is equal to the same thing as lambda u2 v3 minus lambda u3 v2, which is also equal to u2 times lambda v3 minus u3 times lambda v2, so on and so forth, which is equal to u1 cross lambda v1, lambda v2, lambda v3, which is equal to u cross lambda v. Now for perpendicular, we have, when theta is equal to 90 degrees, we have u dot v is equal to modulus of u times modulus of v times cosine of 90 degrees, which is equal to 0. So thus we have u dot v is equal to 0 if u is perpendicular to v. Alright, next up for the scalar product side of the house, we have take note that u cross v is equal to modulus of u times modulus of v times sine theta. Right, so when theta is equal to 90 degrees, we have u cross v is equal to modulus of u times modulus of v. When theta is equal to 90 degrees, or u is perpendicular to v. And for u is equal to v, for the scalar product, we have u dot itself is equal to u1 times u1 plus so on and so forth, which is equal to u1 square plus u2 square plus u3 square, which is equal to the square of the modulus of u. Right, for the scalar, for the cross product, we have u cross itself is equal to u2v u2 u3 minus u3 u2, so on and so forth, which is equal to the 0 vector. Now that we know about the cross product and the scalar product, we can move on to projection, which is about two vectors. Now let's say we have 3 points, the origin, the point u, as well as the point v. We have two vectors u and v. Now the angle between them is theta. The length of projection, now imagine the sun shining from above the point, the line OU, projected onto the line OV. So the shadow of OU on OV would be this red line over here, right, which makes an angle of 90 degrees with this line over here. Now the perpendicular distance from, now let's call this point W. Now the perpendicular distance from U to the line OV is equal to UW, where UW is perpendicular to OV. So the length of projection of OU onto OV is called OW. And it's really important for the word choice to be one onto the other, because the projection of V onto OU would be over here, right? V onto OU would be this line over here. It would be a totally different thing than OU onto OV. So now we're going to derive a formula for the length of projection. And we're using this right angle triangle OUW, where OW is the adjacent, WU is the opposite, and OU is the hypotenuse. We have the length OW, which is the length of projection of OU onto OV, be equal to the modulus of U, which is the hypotenuse over here, times cosine theta, right? And bearing in mind that U dot V is equal to the modulus of U times modulus of V times cosine theta. Right, dividing by V on both sides, we have U dot V over modulus of V, which is also equal to U dot the unit vector of V. Right, it's equal to the modulus of U times cosine theta. So we have this bearing in mind. We have OW is equal to the scalar product of U and the unit vector of V. But this is not the end of the formula, because what if the points OUV form an angle of theta that is more than 90 degrees? Right, so this is O, this is U, this is V. The length of projection of OU onto OV would be this length over here, which is VO produced. Right, so W is on VO produced. In this case, OW is still the length of projection, only that theta is this angle over here, which is 180 degrees minus theta. So we have OW is equal to the modulus of U times cosine of 180 degrees minus theta, which is equal to negative of U cosine theta. Right, and that's equal to negative of U dot the unit vector of V. So the formula, the overarching formula for the length of projection, or the scalar projection of OU onto OV, right, for the matter of fact, the projection of one vector onto another is equal to, the projection is equal to the modulus of U dot the unit vector of V. Or you can also say it's the scalar product of U and V over the modulus of V, whichever is more convenient. And so in another case, we are using sine instead. So in this case, you want to find the perpendicular distance from U to OV instead of OW. So this was the formula we found earlier, U dot V with a hat on top. And using the same train of thought, with modulus of U as the hypotenuse, we have UW, which is the perpendicular distance from U to OV. We have UW is equal to the modulus of U times sine theta. And take note, we have the modulus of U cross V is equal to the modulus of U modulus V sine theta. Dividing by V on both sides, we have U cross V over modulus of V, which also happens to be U cross the unit vector of V, is equal to U sine theta. And therefore, the overarching formula for the perpendicular distance which is the opposite in this case of the right angle triangle, we get UW is equal to the modulus of U cross the unit vector of V, or the cross product of U and V over the modulus of V. Whole thing modulus